Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. Today we have a very special guest, Dr. Jennifer Hoffman, professor of physics working in condensed matter physics at Harvard University. She's going to talk to us today about landscaping at the nanoscale. Hi, Dr. Hoffman.
Hi, Susan.
Thanks for being here today. So, landscaping at the nanoscale. Nano means very, very tiny. So why would we want to move something around on a nanoscale?
There are a number of reasons. I think the most obvious reason that people talk about a lot is to store information. And in this age, we have more and more information, and we want to store it more and more densely. And so the most obvious reason people want to move things around at the nanoscale is to store that information in ever smaller space. But there are many not so obvious reasons why people want to move things around at the nanoscale. Many macroscopic, many big materials that you see actually have their macroscopic properties are dominated by what is going on at the nanoscale anyhow. So even if we aren't actively moving things around at the nanoscale, the electrons in the materials that we encounter in our daily lives are moving around at the nanoscale. And so one thing that scientists do is we try to understand how those electrons are moving around at the nanoscale. And one way to understand how they move around is to actively poke and prod them and move them ourselves and see how they react.
So you can actually poke and prod an atom or an electron. You can't just obviously use your finger because it's too small. So do you have to use something that's equally as tiny?
We do. Essentially, we use something with a very sharp tip. So it's like a needle that's got a little conical tip, and that cone terminates in a single atom. The problem, though, is that even though it terminates in a single atom, it is part of a macroscopic object, and so we have to somehow figure out how to move that macroscopic object with the precision that allows us to move the terminating atom at the nanoscale. So we need some way to couple a macroscopic motion into a nanoscopic motion.
Exactly how big is an atom on the nanoscale?
A typical atom is about half a nanometer.
And how about an electron? That's even smaller than that.
Well, an electron is a point particle, so it actually has no size at all. But it's usually delocalized. It's usually existing in a little cloud. It's moving so fast that you don't think of it as a point particle. You think of it as a cloud of probability of where that electron might be at any time.
And you can move that cloud then?
You can move the cloud around, yeah.
Okay, so we're talking on the nanoscale. You have a little needle-like object that gets so small it's down to the atomic level. How do you then translate that back up into some big mechanical motion? First, you have to be able to detect something. Then you have to be able to move that something.
Mm-hmm. Actually, even in order to detect it, we have to be able to move, because we typically detect something by scanning our sharpened tip across it until we see it. So we're scanning our tip back and forth looking for the feature of interest.
But can you actually see something that's that tiny? Do you get a visual picture of it?
When we say the word see, we're thinking about light going into our eyes. And the wavelength of light is hundreds of nanometers. And that sets the smallest scale for anything we can see with our eyes, hundreds of nanometers. So if we want to see something that's smaller than hundreds of nanometers, we have to reinterpret what we mean by see. So what I do is I use a scanning probe microscope, and I scan a detector around.
Which is that needle.
That needle. So I scan the needle that's smaller than hundreds of nanometers. And so then I map some piece of information at each pixel in an area. So instead of, like, your eyes take in all the information of an entire frame at once. And I can't take in all that information at once, but with my little probe, I can pixel by pixel tell you what's going on and then put all those pixels together and make a map.
Okay, well, that makes sense. And then is that same needle the way that you can now move those atoms around?
Yeah. So the real question that I think you're asking is, how do we control the motion of that needle?
Exactly, on a very, very small level.
So it comes down to a special kind of material called a piezoelectric material. Piezoelectric materials, it's like a ceramic, but it's a special kind of ceramic that actually changes shape when you apply a voltage to it. And that sounds maybe pretty novel if you think about applying a voltage, and you're probably picturing some kind of a, big squishy object changing shape. It's not quite so dramatic as that, right? in fact, we rely on it not being dramatic. We want it to be a very small change in size or shape because that's how we control a very small motion of our very small tip. It sounds exotic nonetheless until you realize that we encounter piezos in our life all the time. A typical doorbell is a piezo material, and what's happening there is you've got this little piece of ceramic and you apply a voltage to it, not just a steady voltage, but actually a changing voltage, a sinusoidal voltage, an alternating voltage. And that causes that little piece of material in your doorbell to change shape very rapidly at an audible frequency, and it sends sound waves that you then hear. So piezos are useful in your daily life. In fact, you can build a scanning probe microscope out of a dissected doorbell.
Wow. Okay. That's pretty interesting. I'm sure there's directions for that somewhere online.
On my website, in fact, yeah.
Oh, what's that website?
You can go to hoffman.physics.harvard.edu.
Cool. And learn how to make your own scanning probe microscope. Very cool. You said in the beginning that there's many reasons why you would want to be able to move atoms around. Why do you, in your research, move atoms around?
I'm interested in the boundary between macroscopic classical properties and microscopic quantum properties. So if you have a single atom, the best way to understand that atom is with quantum mechanics. Whereas if you have a tennis ball, the best way to understand that tennis ball is with Newtonian dynamics. And one way that we can get at that crossover is to start building up structures out of individual atoms and to see when the properties essentially cross over from those which would be best described by quantum mechanics to those which would be best described by a more collective classical dynamics. Even the macroscopic materials that we're familiar with are dominated by the motion of things at the nanoscale.
Okay.
And so, for example, these superconductors that I study, even though the technological applications are all going to be from macroscopic pieces of material, the dynamics that control the macroscopic properties, like how much current you can measure through the superconductor, all of those dynamics are dominated by stuff that's going on at the nanoscale. So if we want a superconductor to be at its most efficient, we need to understand these nanoscale objects called vortices. And one way to understand them is to pull on them, to move them around, to actually measure the forces that it requires to move a vortex or the forces of repulsion between two neighboring vortices. So I think another reason that I'm interested in nanoscience is to understand the invisible groundwork for the macroscopic world around us.
Okay, and one of those examples, so superconductors, which are objects that usually need to be supercooled, and when they are cooled, it's metals that then exert an electric and a magnetic field.
The material itself reacts to an electric or a magnetic field which is applied to it, and if you try to apply an electric field to a superconductor, you can't, because the electrons in the superconductor can just essentially instantaneously rearrange to shield that electric field. Or in the case of a long wire, if you try to apply electric field, you will get an essentially infinite current flowing through the material.
So superconductors are very, very efficient.
They're very efficient. You can flow very large currents with virtually zero voltage applied.
And what's one of the main applications for...
So one of the applications for a superconductor is to create large magnetic fields. And the way we do that is we make electromagnets. The concept of an electromagnet has been around since Maxwell discovered it over 100 years ago by applying a current through a little coil and noting that the coil deflected a compass needle. So that was the first link between electricity and magnetism. And so now we can build very large magnets with very big coils. But if you build the coil out of copper and you're flowing a very large current through the copper, it generates a tremendous amount of heat. So there are magnets like this in the National High Magnetic Field Lab in Florida, but they generate so much heat that they can only be run for an hour or so per day, and then they have to cool off the rest of the time.
And so a superconductor wouldn't be losing all that much energy.
Right. So a superconductor should be able to hold the current forever without dissipating any heat. So you send the current around and then you close a switch. So you now have a closed solenoid, a closed spiral of current that can flow forever without any loss of energy.
And those vortices that you were talking about, though, those can actually cause a small loss of energy?
Exactly.
And so you're trying to figure out how that you can take those vortices and move them so you don't lose as much energy?
We're trying to understand how to get the vortices to stand still, in fact.
Oh.
And the way that we're going to understand how to make them stand still is we're going to look at them standing still, and we're going to see how much force it takes to move them. So we can actually measure in piconewtons. Now, pico is a factor of 1,000 smaller than nano. We can measure in piconewtons how much force it takes to move a vortex. And that's why we try to move them. We try to move them because as we poke them, as we prod them, we can measure how much force it actually takes.
Okay, that makes sense. And then the more you know, if you can keep these vortices in place, then the superconductor is going to become even more efficient, which then can be used for all different types of applications.
That is the goal, yes.
Well, thank you, Dr. Hoffman, for telling us about your work with superconductors and how it is important to understand things at the tiny, tiny scale in order for them to work better at the large scale.
Absolutely. Thank you very much.